water's self-ionization. Ever since chapter 8, we have spent a lot of time on solution-related facts. We studied the behavior of solutions. We studied the unique behaviors when different substances are dissolved in solutions. But one thing we kind of have overlooked is the solvent, the most common solvent of solution, water. So today we talk about water. Water actually by itself ionizes. We call it water self-ionization. Even in pure water, a proton can be transferred between two water molecules. So one water will accept a proton, becomes hydronium ion. The other water will donate a proton, becomes hydroxide ion. And this is an equilibrium. It goes back and forth. Well, you may want to ask, wait a minute, Dr. Yang, are you telling me that now in a beaker of water, there are lots of hydronium ion and hydroxide ions in it? That's not right. There are hydroxide ions and hydronium ions in it. However, the relative amount is very low just because this equilibrium lies far to the left. Majority of water molecules, close to all of them, will stay as water molecules. An extremely small portion of the molecules becomes the ionizes. So this picture shows us the transfer of one proton between two water molecules. One becomes a hydronium ion, the other becomes a hydroxide ion. If we're talking about pure water, then the amount of hydronium ion and the amount of hydroxide ion will equal because they are both produced from the transfer of protons between two water molecules. Every time a hydronium ion is generated, there must be a hydroxide ion. Again, we're talking about pure water. What is the KEQ expression? Okay, let's try to write out the KEQ of this equilibrium. KEQ equals the product of the concentrations of all the products, hydronium ion concentration, multiplies it by the hydroxide ion concentration, divided by the product of the concentrations of all the reactants. Reactants, water. Well, this water here is a liquid. The concentrations of a liquid should not appear in the KEQ expression. Therefore, this is the KEQ of water's self-ionization equilibrium. This is the KEQ of this equilibrium. If you look at this KEQ, you will see that this KEQ is actually the product of two ions. Hydronium ion concentration multiplies the hydroxide ion concentration. It is the product of two ions. We have a unique name for the KEQ of water's self-ionization. This KEQ is called the ion product constant for water because it is only the product of two ions, hydronium ion and hydroxide ion. At 24 degrees Celsius is 1 times 10 to the power of negative 14. The ion product constant for water is represented as Kw. Okay, the W means it is water. This is the KEQ for water self-ionization. Remember, KEQ is only a function of temperature, So as long as the temperature is set, KEQ will not change. So at 24 degrees Celsius, it has been verified that Kw is 1 times 10 to the power of negative 14. Now, if a solution is given and one of the hydronium ion or hydroxide ion concentration is given, then this is how you calculate the concentration of the other one. Hydronium ion concentration is going to equal Kw divided by the hydroxide ion concentration. So Kw equals hydronium ion concentration times it by the hydroxide ion concentration. On both sides, we can divide it by hydroxide ion concentration so that this will be cancelled. So hydronium ion concentration equals that, and that is 1 times 10 to the power of negative 14. Here we go. This is what it is. Are you guys following me? Okay, so hydronium ion concentration equals Kw. Kw is 1 times 10 to the power of negative 14 divided by hydroxide ion concentration. If hydronium ion concentration is given, then this is how you get the hydroxide ion concentration. All right. One more time, no matter what is in the solution, the product of the two concentrations must equal 1 times 10 to the power of negative 14. Okay. Only temperature has an impact to Kw or any KEQ value. KEQ, equilibrium constant, is only a function of temperature. When temperature is set, the KEQ will not change. Therefore, Kw, as long as the temperature is 24 degrees Celsius, Kw is that, regardless what you have in the water solution. What impact will adding sodium hydroxide have to water, to the ion product constant of water, to Kw? Okay, if you add some sodium hydroxide to water, how will that affect the Kw value? Well, it has no impact. Kw will stay the same. Kw will only change if temperature changes. Wait a minute, Dr. Yang. We know Kw equals hydronium ion concentration times by hydroxide ion concentration. Now, if you add sodium hydroxide to a solution, you're adding a lot of hydroxide ion to it. You're increasing the hydroxide ion concentration. If the hydroxide ion concentration is increased, wouldn't the value of Kw increase? That's a very good question. However, the answer is no. Kw is not going to change because when you increase the concentration of hydroxide ion in the solution, the hydronium ion concentration will decrease automatically. This equilibrium when you add hydroxide to it, this equilibrium will shift to the left, so hydronium ion will decrease. Make sense to you? Again, only temperature will change the Kw value. If temperature stays the same, regardless of what you are adding to a water solution, Kw will not change. You add acid, Kw will not change. You add base like this, Kw will not change. Clear? This slide is trying to use a chart to show us the relationship between hydronium ion concentration and hydroxide ion concentration. Remember, Kw equals hydronium ion concentration times by the hydroxide ion concentration equals 1 times 10 to the power of negative 14. Now, the first part of the chart shows us when the two concentration equals, well, if these two concentration equal, the product of the two equals 10 to the negative 14. If they equal, each one is 10 to the negative 7, because 10 to the negative 7 times 10 to the negative 7 equals 10 to the negative 14. So when the two equals, as you can see, the value is right on the 10 to the negative 7 to the power of negative 7 mark. When they equal, that is a neutral solution. In the acidic solution, the amount of hydronium ion concentration will increase. Well, it is using a going down arrow to mean that it is increasing. That's because on the side, if you look at this number, the lower you go, the greater the number. So when the hydronium ion concentration increases in the acidic solution, the amount of hydroxide will decrease. The product of the two will still be 10 to the power of negative 14. In this case, in the acidic solution, hydronium ion concentration will be greater than 10 to the power of negative 7. Hydroxide ion concentration will be lower than 10 to the power of negative 7. Make sense to you? Before, in the neutral solution, they equal. Each one is 10 to the power of negative 7. Now, hydronium ion concentration is increasing, hydroxide ion concentration is decreasing. In the basic solution, it is the opposite of the acidic solution. In this case, hydroxide ion concentration will be greater than 10 to the power of negative 7, and hydronium ion concentration will be lower than 10 to the power of negative 7. This slide summarizes what we just discussed on the last slide. When the two concentrations equals, when the two concentrations equal, it is neutral, and we know that number, the concentration of each one of them, when they equal, it is 1 times 10 to the power of negative 7. When this hydronium ion concentration is greater, it is acidic, and for acidic solution, hydronium ion concentration is greater than 10 to the power of negative 7. Hydroxide is less than 10 to the power of negative 7. Basic solution is the opposite. Basic solution is the opposite. Exercise: calculate the hydronium ion or hydroxide ion concentration as required for each of the following solutions and state whether the solution is neutral, acidic, or basic. All right, let's look at the first one. The first one, hydroxide ion concentration is given. So we are asked, in this case, to get the hydronium ion concentration. Hydronium ion concentration will equal 1.00 times 10 to the negative 14 divided by the hydroxide ion concentration. First of all, we know when we see this number is greater than 10 to the power of negative 7, so we know this is basic already. Now let's get the answer for hydronium ion concentration. 1 times 10 to the power of negative 14 divided by 1 times 10 to the power of negative 4 equals 1 times 10 to the power of negative 10 molarity. Well, the second one is basically you're going to get the second one similar to the first one. I will leave the second one for you to do it. All right, you can pause the video and complete the question. Calculate the concentration of hydroxide ion for it. Answer the question whether it is acidic or basic. Once you're done, unpause the video, check the answer key. Here is the answer key. See you next time.